Hi, my name is Aryan Garg, and this is my Physics 2211 Lab 3 on black hole and orbits. So let's start this lab. Talking about the purpose of this lab, the first purpose is to analyze a star's orbit around a black hole and then estimate this black hole's mass using Newton's law of gravitation. For the second part, we want to simulate a moon and a spaceship's motion around this planet and then predict their orbital motion without the spaceship crashing into either. Talking more about the main result before we dive right in is we estimated the black hole's mass to be 1.095 into 10 to the power 34 kilograms. We also saw that the moon orbits the planet, obeying the laws of gravitation, and the spaceship's path under both the planet and moon's gravity does not collide with either of them. The physics model for the same relies on Newton's second law, which is the net force is equal to mass times acceleration, and Newton's law of gravitation, which is F is equal to g m1 m2 divided by r squared, which in our cases would be the mass of the planet as well as the thing orbiting the planet. We assume a system of, for part one, we assume the system of a star orbiting a black hole, and we make two assumptions: that A, the black hole is at origin, and that there's only gravitational forces acting on the star. Our orbit visualization looks something like this. A major challenge here was understanding the scale as well as the visualization to represent the arrows in the best way possible. And as you can see, the star orbits around the black hole in a complete orbit. We calculated the mass of the black hole in the following way. First, we know that force is equal to delta P divided by delta T, which basically just means the change in momentum over time. Now, the momentum, as we know, is equal to mass times velocity. And hence, this net force, well, by substituting the formula, could be written as mass times change in velocity over change in time. Now, using the laws of gravitation, we know that the force is equal to the g constant multiplied by the mass of the first body into the mass of the second body divided by the square of the distance between them. And hence, by substituting this value and moving all the alternative values onto the other side, we can see that the mass of the black hole can be calculated by the equation F times r squared divided by g times m. And on the bottom of this slide, we can also see the actual screenshot from GlowScript, which puts this formula into practice. The final result, as we discussed, is the average black hole mass is calculated. Now, a word of caution is that this is the average mass, which means there were a bunch of values, and after the simulation was complete, the average of those mass values was calculated and displayed. Now let's dive into part two, which places our new system as a combination of the planet at the origin, our moon in that planet's orbit, and a spaceship that is launched from the moon. Our main goal here is to find the initial velocity, which basically leads to an orbit that is A, under the influence of both the planet and the moon's gravitational force, but also does not collide with them. The forces at play here are, for the moon, on the moon, there's a gravitational force of the planet and the gravitational force of the spaceship. And on the spaceship, there's a gravitational force of the planet and that of the moon acting on it. The net force on each of these objects is just the sum of these gravitational forces. An orbit visualization for us in this part 2 case looks something like this, where the magenta shows the spaceship's orbit, the cyan is the moon's orbit, and the blue dot represents the planet. I ran the simulation for 2,450 hours just so the moon could complete a full orbit. Our results were like this. The moon's orbital speed we found was 616 meters per second, and the orbital period was 2,350 hours. Our spaceships was following an orbit throughout the whole time without crashing into the planet or the moon. Now, diving into the additional questions, this means that the net force leads to a change in momentum over time. This force is caused by the gravity from the black hole, and this rate of change of momentum changes the star's motion over time. The parallel component of this force changes its speed, as well as the perpendicular component of the force changes the star's direction. For the part 2, we know that all the objects in the system, the black hole, star, planet, and moon, experience gravitational forces. There are different combinations of these forces possible, namely black hole and star, star and planet, planet and moon, moon and spaceship, and planet and spaceship. The net force is just equal to the sum of all these gravitational forces for each object, and then the motion can be modeled using F equals ma. Sources of error for this project could stem from approximation errors, precision errors, incorrect assumptions here and there, and some other missing gravitational influences that may act in real life. To conclude, we know that the motion in orbit can be explained by Newton's law of gravitation. We successfully estimated the mass of a black hole, and we modeled real-world scenarios and understood that they have complex interactions. Thank you so much.